Okay, we are winding down here and getting close to the end. We talked not as much as I would like, but as much as we're going to about the Big Bang Theory as a theory about the history of the universe. And that theory says, in short, that everything in the universe on the large scale, meaning galaxies and superclusters of galaxies, is moving away from us, and everything is moving away from everything, which means the universe is getting bigger, which means in the past, the universe was smaller, 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 smaller as you go back in time. What we want to talk about now is what happens next. Where's the expansion of the universe headed? And there's only a couple of possibilities. One is that the universe just keeps expanding forever at its current rate. The term that we use to refer to a universe that expands forever in general relativity is an open universe, meaning in the distant future, there is an infinite amount of space in the universe as the universe gets bigger and bigger and bigger. Another possibility, however, is that the expansion of the universe stops and the universe collapses again. Why would this happen? Well, everything in the universe is being gravitationally pulled by everything else in the universe. And if the gravitational pull of everything in the universe is big enough, just like if you throw a ball up in the air, the Earth's gravity pulls it back down. If the Big Bang threw everything in the universe in this expansion and gravity is strong enough, it will pull everything back together. A universe that collapses and never has an infinite amount of space in it before it goes away again, or whatever happens at the end, it's called a closed universe. So those are the two options. The universe can be open or it can be closed. The name that's often given to the collapse of the universe, the hypothetical collapse of the universe, is the Big Crunch. For a while, some astronomers tried to call it the Gnab Gib as kind of a joke, but that term never really caught on. So if the gravitational pull of everything in the universe is going to slow down that expansion, cause it to slow down again, there will be a big crunch. That is the reverse of the Big Bang, where the universe gets smaller and smaller and smaller and denser and denser and hotter at some point in the distant future. There is also a borderline. Do I have a slide for that? Maybe I don't have a slide for that. There's a borderline between these two possibilities. One where the universe gets bigger and bigger and bigger at its constant, basically constant rate, and one where it gets bigger and bigger, it slows down and collapses. In between there is if the universe's expansion is just at the borderline, so it slows down and slows down and slows down, so it's always slowing down but never quite stops completely, that's called a flat universe. And the flat is a reference to the fact that in general relativity, the curvature of the universe at that distant point in the future will be zero. So how do we know which of these following futures is the future that the universe will experience? Well, the answer is just depends on how much stuff there is in the universe. If there's not much stuff in the universe, if there's not a whole lot of mass, then the gravitational pull between distant galaxies won't be enough to reverse their motion away from one another. And so the universe will expand forever. If there's a lot of stuff in the universe, then the gravitational pull of everything in the universe will be enough to slow down those galaxies and make them collapse again. And there will be a big crunch, and the universe will be finite in time and finite in space. So, naively speaking, all we have to do to figure out if the universe is going to expand forever or stop expanding and collapse eventually is to just measure how many galaxies there are and how much a galaxy weighs and see if there's enough stuff in the universe to slow down its current rate of expansion. The density of the universe that would put it right on the borderline, this flat borderline between expanding forever and collapsing again, is called the critical density. So if the density of the universe is less than the critical density, it will keep expanding forever. If the density of the universe is greater than the critical density, it will expand until gravity starts to win, and then gravity will cause a big crunch. If the density of the universe is exactly equal to the critical density, it will slow down and slow down and slow down and get slower and slower and slower, but never quite come to a complete stop until an infinite amount of time, if the density is exactly equal to the critical density. Okay, so this is the situation. If we live in a universe where the density is equal to the critical density, the universe will expand forever. It will be flat. It will slow down at just the right rate so that it takes it an infinite amount of time to stop completely. If the universe has more matter, its density is greater than the critical density, it will eventually slow down and recollapse. There will never be an infinite amount of space in the universe. There will always be a finite amount of space in the universe. And so the answer as to which of these two possible or three possible versions of the universe we live in is simply governed by how much stuff there is in the universe, how much matter there is in the universe. So, how much stuff is there in the universe? What is the mass of the universe? Can we weigh the universe? Well, we said we can tell how much a galaxy weighs. We know how many stars are in a galaxy. There are a couple 100 billion stars in a typical galaxy. We know how much a typical star weighs. Our sun weighs 2 times 10 to the 30th kilograms. So that's what? A million trillion kilograms. If we naively just take our pictures of the sky and count up the galaxies, there's a few 100 billion of them. If we multiply that by the number of stars in a typical galaxy, there's a few 100 billion of those. So the calculation looks like there's a few 100 billion galaxies in the universe. There's a few 100 billion stars in each galaxy. We know the mass of a star, so that should give us the mass of the whole universe. A few billion times a few 100 billion times 2 times 10 to the 30th kilograms per stars gives us a huge number, right? 4 times 10 to the, 11, 9, 10 to the 50th. I don't know. It's a big number. We don't care about the number. What we care about is what is the result. Is that enough mass to reverse the Big Bang expansion? The answer is no. If we count up how much stuff there is in the universe that we can see with our telescopes, and that is important. We count up how many galaxies we see with our telescopes. We count up how many stars we see in a typical galaxy. We multiply those by each other. We get a density that is much, much less than the critical density, a mass that is much, much less than the amount of mass it would take to stop the Big Bang and reverse it into a big crunch. So based on what we can see with our telescopes, it looks like the universe will keep on expanding forever. Is that the end of the story? No, that's just the beginning of the story. Because there are reasons, theoretical reasons, why scientists were hoping is not quite the right answer. Suspected that the density of the universe might be exactly equal to the critical density, the exact amount of density necessary to stop the Big Bang expansion, but not reverse it. Why is that? Can I explain why that is? Do I have a slide explaining why that is? Yeah. It would be a very nice result if the universe had just enough mass in it to slow down its expansion, but not stop it. One of the reasons it would be a nice result, and this is getting a little off track, but it's an important idea. It's probably not true, but it's an important idea. Look, one of the crazy things about the fact that there's a universe at all is that there's a law of physics called the law of conservation of energy that says you can't create matter and energy out of nothing, that matter can create energy, energy can create matter, energy can beget other energy. But if energy is conserved, you shouldn't be able to create a whole universe of energy out of nothing. And it looks like what happened at the time of the Big Bang event. Now, maybe it's okay that the Big Bang event violates conservation of energy. After all, if there was a cause of the Big Bang event, it couldn't have come from our universe because our universe didn't exist yet. Maybe our universe is living on energy that was borrowed from outside of our universe somehow. But there's another answer that's a little more satisfying, which is this. Things with velocity have kinetic energy. That's positive energy. Things with mass have equals mc squared energy. That's positive energy. Things with that are hot, that are giving off heat, have thermal energy. That's positive energy. Light has positive energy. Okay, if I point my camera at the window. There's a bunch of sunlight coming in my window. That all counts as positive energy. And we just add it up. Gravitational attraction between objects and electrical attraction between objects counts as negative energy, negative potential energy. In order to pull two things apart against the force of gravity, I have to put energy into the system to pull them apart, which means the energy holding them together counts as negative potential energy. It turns out that it's possible that if all of the mass energy in the universe plus all of the kinetic energy of that stuff away from each other is exactly equal to the gravitational potential energy, which is what it would mean for that gravitational potential energy to be just enough to stop it. It's possible that the total energy of the universe could be zero. That if you add up all the positive energy, the kinetic energy, the thermal energy, the photons of light, the mass, and its motion on one side of the equation, and you add up all of the attractive gravitational energy pulling everything towards each other, it's possible that if the density of the universe was the critical density, the energy of the universe could be zero, and then the creation of the universe didn't violate the law of conservation of energy because the universe doesn't have any energy. Or rather, it has just as much negative gravitational energy as positive kinetic and mass energy. Again, it's looking more and more like that's not true, but at the time, and what's the time? Let's think of this as being like the late 1980s. Scientists wanted the universe to be a little heavier, so they thought, well, let's check and make sure that our estimates of the mass of the universe are right. The way to do that is to carefully measure the masses of galaxies. We talked about how you would do this. You observe the rotation of the stars in a galaxy. You measure the Doppler shift of stars on one side, compare it to the Doppler shift of stars on the other side. That measures the speed of rotation, and you can use Newton's law of gravity. If you know how fast the stars are orbiting, you know how big the galaxy is, you can calculate the mass of the galaxy. We did this for a bunch of galaxies, starting in the 1960s all the way through the 1980s and 90s. We measure the rotation, we calculate how fast the stars are orbiting, and we calculate the mass. And what we find when we do that is that almost every galaxy we observe is rotating faster than we would expect it to be, given the number of stars in it. In other words, the more stars are in a galaxy, the greater its gravitational pull on the stars on the outskirts, and the faster they will be able to orbit, or the faster they will have to orbit in order to stay in orbit around the galaxy. If the mass of the galaxy is small, then galaxies in the outskirts will be moving slowly to stay in orbit. Every galaxy we look at seems to be spinning too fast. Too fast for what? Too fast given the amount of starlight that we can see coming from it. In other words, if we estimate the number of stars in a galaxy by measuring its brightness and how much light it gives off, and we measure the mass of a galaxy based on its gravitational pull and how hard it seems to be holding its stars in orbit, the galaxies seem to be more massive than we would expect them to be just based on the stars that we can see. We say this in a few different ways because it's a really important idea in astronomy. When we compare the brightness of a galaxy and the gravitational pull of the galaxy, the brightness of the galaxy tells us how much starlight there is. The gravitational pull of the galaxy tells us how much mass there is. There seems to be way more mass than can be accounted for by just adding up all the stars we can see. So a typical galaxy might have 100 billion stars worth of light coming out of it, meaning we would assume that there are hundreds of billions of stars in it. But the mass of that galaxy turns out to be 1 trillion stars worth of mass, 10 times more, sometimes even tens or hundreds of times more. That suggests that the mass of a galaxy is not just the mass of its stars. That when we're measuring the mass of a galaxy, we are getting a bigger number than we would expect, which suggests that there is something in that galaxy other than the stars. Not just that, but that something could make up as much as 90% of the mass of a galaxy. That 90% of the mass of a galaxy is something that's not stars. What is it then? We don't know. The name, the label we give to this, whatever it is in galaxies that is increasing its mass but not increasing its brightness, is dark matter. Dark matter is not a kind of stuff, not yet anyway. It is a placeholder for the fact that we do not know what the stuff is in a galaxy, causing it to have more mass than we think it should have, more mass than we would guess it would have based on just its starlight. Okay. So the dark matter problem says that maybe 90% or more of our universe consists of some kind of stuff that we're not seeing in our telescopes. It's not contributing to the brightness of a galaxy, hence dark matter. Okay. It doesn't give off light. What is dark matter? We don't know. Do we have any ideas? Sure, we have ideas. We have lots of ideas, but we just don't know which ones are right. What could the dark matter be? What could have mass but not give off light? Well, we've talked about some weird little particles in this class already that have a little bit of mass, and the room you're in is full of them, but they don't give off light because they don't have any electric charge and they don't interact with matter very much. Those particles were called neutrinos. We talked about the fact that nuclear processes give off neutrinos. We detect hundreds a day in our particle detectors. We know they're real. They're going through your body right now, going through the earth and coming out the other side. If neutrinos have a tiny bit of mass, and you add up all the trillions of neutrinos in every cubic centimeter of galactic and intergalactic space, that could add up to a whole bunch of mass. Is it enough mass to be the dark matter? It doesn't look like it. It could be some of the dark matter, but probably not all the dark matter. But what if there was another particle that was like a neutrino in that it has no charge and it doesn't interact strongly with protons and neutrons and electrons, and the room you're in is full of them and they're going through you right now, but instead of having a tiny mass like a neutrino, they have a great big mass, as much as a proton, as much as a carbon atom. Who knows? So dark matter could be some little invisible particle that we have not ever detected yet that has a mass but doesn't interact with light. How would we know that this is what dark matter is? We would have to detect one of these particles. There are searches going on in particle accelerators for particles that have this property, lots of mass but weak interactions. Actually, the name for these particles is WIMPs, weakly interacting massive particles. We've never found a WIMP yet, though, so we don't know what they are. And maybe that's not what dark matter is at all. Maybe dark matter is something big instead of something tiny. What about brown dwarfs? What's a brown dwarf? A brown dwarf is one of these things that's kind of in between a planet and a star, like a super Jupiter, but not big enough to have fusion. So it has a lot of mass, maybe 10 times as massive as Jupiter, but not as enough mass to make it a star. Maybe galaxies have a bunch of brown dwarfs in them, and because they don't give off light, we don't see them in our visible light telescopes. Well, maybe, but how many would they have to have if brown dwarfs weigh less than a star and the mass of a galaxy is 10 times bigger than the mass of stars? Then there would have to be 100 times as many brown dwarfs in the galaxy as there are stars. That's not true. If that was true, when we looked up at the sky at night, we would see brown dwarfs going in front of the stars and blocking out their view all the time. We can put limits on how many brown dwarfs there are in the galaxy, and there's not that many. So brown dwarfs could be some of the dark matter, and neutrinos could be some of the dark matter, but probably not all the dark matter. This is why this question, this open question in physics and astronomy right now, is called the dark matter problem. None of the explanations we currently have for what dark matter might be seem to explain all of it. And the answer is we just do not know. And this is one of the big unanswered questions in physics right now. And the other possibility is it could be something else. It could be something we haven't thought of yet. It could be microscopic black holes, which have a lot of mass, but are tiny, 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 so that we would never see them interacting with anything. We don't know. And it's okay that we don't know. If science doesn't have a handful of things that we don't know the answer to, we have no guideposts to point us in the right direction of how to improve our theories. So the dark matter problem is a long-standing problem in physics. Like I said, it dates back to the 1980s or earlier, so say 40 years or so. And we're still trying to figure it out. But we can go back to the question of what does this say about the expansion of the universe? If we now, instead of just taking the mass of what we think a galaxy should be, we take the mass of what a galaxy really is, all the stars plus all the 90% of dark matter that we can tell is there, but we don't know what it is. If we add all that up, then is there enough mass in the universe to stop the Big Bang expansion and reverse it into a big crunch? No, there's still not enough. Even if we take all that dark matter, that invisible whatever that we don't know what it is, and add it up, it doesn't seem to be enough to close the universe, to stop and reverse the Big Bang expansion. So the answer from extrapolating the expansion of the universe into the future and calculating what effect gravity should have on that expansion says the universe will not reverse in a big crunch. Is that the end of the story? Well, no, it's not the end of the story, as is often the case when I reach the end of these videos. Because there's another way to answer this question about whether the universe will expand forever or slow down and collapse again. And that's because we have this thing we get to do in astronomy, which is to look back in time. By looking at very distant galaxies, we're looking at light that came at us billions of years ago. So let's say that gravity was slowing down the expansion of the universe. What would we see when we looked at distant galaxies? We would see that they are not moving as fast, or no, what would we see? If the universe was slowing down and we looked at the galaxies in the past that are super far away, they would be moving faster than we would expect because the universe has slowed down since then. So we can look at distant galaxies and look into the past and ask ourselves, okay, has the expansion of the universe slowed down due to the gravitational pull of everything in the universe? Because we get to look at galaxies 10 billion years ago if we have a big and powerful enough telescope. We've done that. And the answer we got is not an answer that anyone wanted. And it is another outstanding and unanswered question in physics and astronomy. So the dark matter problem is this one. And the next one is called the dark energy problem. And I will talk about dark energy in the next video.